Okay, everyone. So welcome back to second session on modeling. Can you hear me properly? I haven't used my earphones, so I'm using the microphone of the computer. Can you hear me fine?
Yes.
Okay,
Yes.
so I won't use
Yes.
that. That removes one potential problem of the thing falling down. Okay, breaking apart. So. While I do it again in front of everyone, I'm going to see what I've done here is I've created a little file here. I'm going to remove you from my screen, which has the Docker command all typed out properly. Okay. And I just wanted, for those of you who haven't done it, this would be the syntax here with the D. This would be the syntax for a PC. And beware that, you know, a drive name or a folder name on a PC involves a colon and a backslash. And for that, you know, it would interact or interfere with the Linux command. And therefore you need to put your drive path or your volume path between inverted comma. Okay. But here, that's not what I have. I'm going to put mine, it's because I have a Mac, which is users, and I put it in 10, and I created a Dragonstone directory. Okay, so I'm going to copy this, which I have in a small file. I'm just checking in, reading it the last time, and I'm going to put it in my terminal, run it, and open my Docker. So either you have already done it, or you should do it. And don't forget, as I said yesterday, if you killed or if you finished your session yesterday, before you can run the Docker again like this, you have to issue a Docker stop Dragonstone and Docker rm or remove Dragonstone, and then only you can restart the Docker. Okay, so basically you have to kill the computer you were using yesterday or before you can create a new mini computer or fake computer. So I'm going to go back to my browser and reopen my Jupyter lab, and I'm back where I was yesterday. You see, is the font big enough? I can make it a little bit bigger. Yeah. And I'm going to make this window big so you know it looks big on your screen as well. So one last thing, you remember, we must go now into my local drive. This is where the notebooks that are on my hard disk that I can modify and will be saved are. One thing I thought I would do, I'm gonna put you to see a few faces, otherwise I feel so lonely. So I don't know who's gonna be there randomly, guys, but I still need to see that someone is alive at the other end, otherwise I'm crazy. So what I want to do, I thought I should have done yesterday, but I'm going to go back into opening a terminal. So you can always get to this by clicking on plus, and that should open this launcher. Okay, and I'm going to open a terminal like this. Okay, and what I'm going to do is I'm going to copy the notebooks that are in the small computer, the one that we don't work with, so the original notebooks. I'm going to make another copy on my local drive, but I'm going to put that in something that I'm going to call notebooks underscore original, something like that, another name than notebooks. And by doing so, I make another copy of the original notebooks, which I won't modify, onto my hard drive. Oops.
Joel?
I have to put a -r because it's a directory. So we want to do it recursively for all the subdirectories. There it's done. And now if I go into my local drive, you see I have my notebook. I have to because I've done it yesterday. So I'm going to, I've already done it twice here. I want to go original and original because I was trying to do it yesterday, make sure it worked. So I have two originals notebooks and I'm not going to touch them. Okay. But we're going to work on these notebooks that I copied yesterday. Look on my local drive notebooks. But if I do something to a notebook here and it stops working and I don't, oh my God, I can't go back to make it work, all you need to do is go back to these original notebooks here, either of these two copies, and look at the original one where the mistake comes from, because I know these are working. Okay, so let's go back now to the mountain source and quickly let's jump directly, I believe. No, we've done everything in this second one, the FastScape source to sync source _2, which is the basic use of FastScape. And we've played a bit with this, so I'm quite sure I'm going to run it again to make sure that it kind of works. I'm going through all the steps by simply shift return through all the cells of the notebook, and I want to get to the final one. So I've run many models here. Well, that's a long one. It's going to take 10 seconds, so we'll wait a little bit. But what I want to get is to I hope I haven't removed it. I've done so much thing. Is this one here, the topo is 3D. So we'll wait a little bit. Can I assume that everyone now has this working on his or her computer?
Jean,
Yes?
I cannot read the text. It's too small.
I see. Yeah.
So, is this the second or the third one?
I see. Yeah. Okay. It's not too small. It's because you can't sit because I haven't made this big enough. I've opened the second.
Okay.
Yeah. Okay. So this is just the one we did yesterday. We're not going to do anything into it. I made it very long because I made a lot of times. I'm going to be terrible. Why is it taking so long?
Because you changed the area yesterday evening, so maybe that's the reason.
Look, one thing I'm going to show you. I don't want to wait because I'm a very impatient person. So if you hit that little thing, it says interrupt the kernel. If you do this, it'll stop whatever it's doing. Sometimes you have to hit more than one time. And if it doesn't stop, maybe sometimes the kernel is gone on its own and doesn't want you to stop. Okay. What you can also always do is go here, where it says kernel, interrupt kernel, or restart kernel, and that will force a restart of the kernel. Okay. The kernel is the Python thing that's doing the job for you. So I'm going to quickly change that. Thanks for your comment. And now it's go very fast. And I can do what I wanted to do.
Jean, I have a question. Yesterday when I did it, it crashed multiple times. I didn't put any big numbers or something, and I had to restart everything like multiple times. Do you know what it could have been?
No, I would need to see when this happens, Caroline. You should go in the terminal.
Okay.
You submitted you started the Docker, and there should be some message that comes out.
Okay.
And the information is there. If you don't understand it, make a screen copy and send it to me.
Yeah. Okay. So I'll do it next time.
It won't happen. All I wanted to do is, this 3D viewer that you have here. You'll notice that I have commented out. Now I'll go back to a single person here. You'll notice that I commented on a few lines. I will put them back on and explain to you very quickly what they are. You'll see what I do is I create a 3D viewer with my model, ds_out, and I specify the size of the 3D viewer. And also, as I told you, you have to specify what name you have given to the time dimension. Okay. But before I show it, which is this command here, I say, look, I like the background color to be light gray. I like to start with a vertical exaggeration of 5, and always start. This means go to the last time step. Okay. So if you do that, what you see is maybe a more interesting information, because you see now the vertical exaggeration is by default on 5. I'm looking at the last time step, and the background here is gray, which is better than the white. I think you see better what's happening. Okay, but everything works. I can still play the animation as I did before. Okay. One last thing that I realized that I skipped a little bit too fast is something about arrays. Okay, so what is that I need to tell you And to do this, I'm going to, randomly open another. Before we go to the next exercise, I want to take 1 minute to show you something. So I'm going to go in my notebooks here, okay, and I'm going to create a very simple notebook. So an empty notebook, okay. So I click plus, and I create a Python 3 notebook. It's an empty notebook, okay. So I'm going to simply do the classical import numpy. I'm not even sure I need it, but just to make sure I have it, okay. And then I'm going to need it. It's fast. I'm going to create an array, which as usual I call X, okay? And I'm going to go between 0 and 1, and I'm going to put 11 numbers, okay? So here it is. I can look at X, and that's what it is. Very simple, okay? One thing I wanted to tell you is that if I type X like this, I see the whole array. And if I create, say, for example, Y equals X squared, and look at Y, it has created an array that's the same shape as X, where all the elements are just the square of what was in X. Easy, okay? But what I can also do is look at X. I can look at the first element, okay? I can look at the second element, okay? But you notice that in Python, when I say 0, I mean the first, okay? So Python names things, the label it has given, or the index it has given to the numbers here, 0, 1, 2, 3, etc. So the last, even though I asked to have 11, the last one is 10, okay? If you ask for the last one by asking, I want the 11th one like this, it's gonna tell you, I can't, there's only 11 things. And when you ask for the number 11, it's the 12th one, in fact, okay? One way that, you don't have to remember that is to say, well, show me the -1, and -1 is always the last, regardless of the length, okay? But what you can also do is say, look, I want to look from 0 to 5. So it's going to show me 0, 1, 2, 3, 4. It doesn't show me the last. So if I say from 0 to 5, it only goes from 0 to 4. It does not show you the last, okay? So I can do this. This works because it doesn't try to show me 11, it stops at 10. Don't ask me why, that's the way it is, okay? What you can also do is say, look, I only want to look at every second one. So I want to go from 0 to 11, but only to 10, but only show every second one, or every third one. Oops, sorry, third one, okay? What you can also do is say, I want to go from 0 to 5, but you don't have to say 0. If you just say column 5, it assumes that you mean 0. And if you say from 5 to nothing, it assumes from 5 to the last one. And if you say this, it'll show you everything. But you can also say this every second. Everything every second. And most importantly, this is a bit crazy, but you can say this from the first to the last by a step of -1. And what it will do then, it will show you the array in reverse order. Okay? So this way of indexing arrays in Python and in NumPy here is very important to know and to remember. And the only way to remember it is to do what I've done a million times. It's the only way this will get into your scale. Because, for example, me coming from Fortran, x of 0 does not exist. Okay, it's x of 1. And so I'm totally confused when I do Python. And I need to come back to this all the time. I think MATLAB is also x of 1, isn't it? The MATLAB users.
Yeah, I think so.
Yes, it is.
Yeah, so you'll find it so frustrating, okay, that when you say this, it actually means that, okay? And when you say that, in MATLAB, you would actually say something like this. Okay, it's just crazy. All right, but let's not discuss that. We will have to remember and use that. Okay, so keep this little thing, play with it. The good thing with notebooks like this or MATLAB too is that it's super interactive, so you can test things before you put them in your code. Okay. No question on this? Now, let's go to the next. Now we're going to do something useful, and I'm going to make you work. All right? So there's a bit of theory here. I assume you can all see it, and we're going to go very slowly and simply through this theory. Sebastian has done most of it already. Okay? And then we're going to do something here, build a model. And we will build it together, or I will give you some time to build it yourself. So this theory here is back to the stream power law. Okay, that says that the rate of change of topography is proportional to uplift minus erosion. And erosion is assumed to be proportional through this constant Kf to drainage area to power m, slope to power n. Now, what we're going to do is demonstrate that we can run a model to steady state. We're going to use FastScape. Okay? And in the case of steady state, the topographic height is not changing. That's the definition of the top of a steady state. So in that case, the rate of change of topography with time everywhere on the landscape is 0. And therefore, we can write this relationship. This is the one that Sebastian has used to show you that at steady state, the slope must decrease from the source to base level because the drainage area increases from the source to base level. And the product of the two, because this is 0, the product of this by this must be equal to u divided by kf, must be a constant. Now, I'm going to do a little bit more, and Sebastian has mentioned that too. I'm going to use Hack's law. Okay? Hack's law says that the drainage area increases roughly as the distance along the river profile to the power 2. Or here I'm going to use this general Hack's law by using a parameter p. Now, note that I'm using L minus S because for me, S is the distance from the bottom of the profile, from the base level. And so if you want to write Hack's law using S, you can't say Ks to the power p, it's L minus S, okay? Because S is at the bottom of is 0 at the bottom of the profile. So at 0, I have the maximum drainage area, which is K times the length of the profile of the river to the power p2, okay? I want to do this, and I'll use similar one. So I'm going to write this equation now, okay? I put u on this side, and I divide by kf. I put a, I replace a by this in here, and I divide again by a, by this expression, and I reorganize all the terms. I don't want to do it with you now. Believe me, it's correct. You get that the slope must be equal at steady state to u divided by kf, k to the power n, the whole thing to the power 1 over n, times L minus S to the power minus MP over n. That's what it should look like if we assume Hack's law. And you'll see that as S equals to 0, okay, the slope is very small because this is a negative power, so it's 1 over this. Whereas if S is equals to L, we are at the source, this term goes to 0 because it's 1 over, because it's a minus power, this goes to infinity. Okay, so stream power law predicts an infinite slope near the divide if you use Hack's law. So very steep and 0 slope as you get to the source. Now, what's really interesting, and I'm not going to do it now, is that you can solve this equation. If I know that the derivative of h with respect to s is equals to a constant 1 over L minus S to the power n p over 1, you can show that this is the solution of that equation. Okay, no worry, I don't want to do it with you. It's a simple derivation to do. Okay, you just have to go back to your basic function analysis. But what I want you to look at is the shape of that formula. What's really, really interesting is that we can divide it into two parts, this part and this part. This part is where I put everything that has a physical meaning. The length of the profile, U, the uplift rate, Kf, the erodibility, and Km, the constant here for the Haxel coefficient. This part only depends on one thing, S over L. It's the relative position of where I am along the profile. That number is between 0 and 1. At the source, it's 1, and at the exit point, it's 0. So whatever the length, okay, this always varies between 0 and 1. So it's independent of the length, because I've divided the length by the length. It's dependent of the length. This number only varies between 0 and 1, which means that this part only depends on one thing, MP over N. Only depends on the powers, M, N, and P. And we kind of think that P is about 2, so really it's the function of N over N. And what we're going to do now, we're going to run the next cell very simply. And what I do here, I'm just plotting this. Okay, I will plot this function. Okay, so what I do, I say M equals 0.4, N equals 1, just to take a number, and P equals 2. And I'm going to plot an X versus Y. Okay, and X is a number or an array that varies between 0 and 1. There's 101 values. Could put 1,000 if you want to, doesn't matter. And this is exactly this part of the formula, the geometrical part. Okay, it's my number here, S over L, that varies between 0 and 1. I do 1 minus that. This 1 minus the whole thing, I put it to this power. Oh, sorry, I have a mistake here. It should be like, yeah, it's correct. 1 minus this to this power, and then the whole thing divided by 1 minus P over L. That's correct. Okay. So if we plot this, this is what we get. We get this concave up profile, and then we know the solution goes to infinity. So this part of the profile is meaningless. The last little bit here, it doesn't correspond to anything physical. And in the real world, we know that as we go very far to the source of a river, another process will kick in, which has to do with the formation of alluvials and the formation of colluvials, and the hill slope process towards the divide. So we don't care about really this part of the profile, but this one shows you a classical profile for a river. Now, the height of that profile is really bizarre. It's 3. Okay, that's because to get a real height, we must multiply it by these physical constants, U over Kf, K to the power m 1 over m, and that will give me the height of my profile. Okay, in meters, 3,000, 5,000 meters, depending on the value of U, K, and K. And here, this varies between 0 and 1 because I've normalized the distance along the profile by the length of the profile. So you can think of this as 0 to the end of the length of the profile. If it's a 10-kilometer long river, that's between 0 and 10 kilometers. Okay? So what I'm going to do now is check that FastScape is able to reproduce such a theoretical profile by running a FastScape model. Now, we've done this before, okay? We're going to load FastScape and do something with it, and then create a setup. You'll see that the same cell appears twice. And that has something to do with how these cells and these notebooks were put into the container, the Docker container, or the Conda environment that we have created. So we're going to erase all this. I want you all to erase this one. Don't worry. So this is the first of the 2 cells that look identical. Just remove this one, okay? And we will create an empty setup, okay? So we will do that. And then we will compare it with the solution which is down there. But we're going to do this progressively together, or you're going to do it. I want to show you, before going further by running a FastScape model, something really useful that is possible thanks to Benoit's framework. Okay, I remind you, we're going to run this cell, which imports XMLab, Xarray, load these extension, which we know are useful, and load FastScape. Okay, so nothing really happens. Okay, it just loads all of these things. I want to look at this basic model that we used yesterday. So if we want to look at it all together, let's add a cell here, and let's look at basic model. All we need to do is just type basic model, hit shift return, and we see what it's inside the basic model. We did this yesterday. And I mentioned to you that there is this process called diffusion, which is the hill slope process, which we don't want to deal with today. The great thing about the framework that Benoit Bovier has developed is that we can easily, okay, I don't want to have a process that deals with the diffusion on the hill slopes, let's just remove it. And so what you can do is create a new model, give it a name. I've called it SPL model, and it takes the basic model. And that is one of the things you can do to any of the FastScape model is this thing called drop processes, and we drop diffusion. Okay, so I look at what is in basic model. I don't want this process of diffusion. I'm going to drop it. So if I run this cell, again, I don't really need to. And now, instead of basic model, I look at SPL model. Okay, let's look at it. SPL model looks exactly the same, but now diffusion is gone out. And if we visualize the SPL model, it's got all the bubbles, there is a bubble missing, that's diffusion. And what this operation, drop processes has done, it's removed not only diffusion, but all the links to diffusion and the others, all the variables that are only needed by diffusion, and maybe potentially to some processes that are only needed by diffusion. And so that there are no bubbles left alone in this, and no arrows that point to something that doesn't exist. Okay, so it's done all that very cleanly for us. All right. So now we all have this SPL model. You can call it whatever you want, my model or just model. Okay. You do this in this command here. The name that you give here is the name of your new model. And now we're going to run this line, but to do this, we remove the dash, okay, the hash sign, which in Python, is comment. Okay, and I remind you that if we run this command, and I propose to all of you to do it, it's going to create a setup for this model, but an empty setup, and together we're going to fill it together. Okay, so let's run this command, and we should have now, it's basically this command has written something in the cell for you, okay, which is a bizarre thing that these extensions do, these Jupyter Lab extensions do, and it has commented itself out as well. So every time we run this cell, it doesn't re-empty what it's just done. Okay.
Jean, can I ask a question?
Yeah.
What does the percentage symbol means before the create setup command?
Yeah, it tells the cell that this is an extension for the cell. It's not a Python command. It's something that it sends to Jupyter Lab, the guy that's running the cell, and it tells it to do something with the cell.
Okay.
It's not doing any Python.
Okay.
It's called an extension to Jupyter Notebooks or Jupyter Labs.
All right, thank you.
Don't ask me more than that. I don't know how they work. That's what Benoit told me.
Okay.
So, and then we have, our setup, which is empty. And if you, on your own, want to use FastScape to try your own ideas, I suggest after a while that you do this and start exploring what you can do with this. You'll have to get used to the syntax, but it's not that complicated. Okay. So you take a few minutes to fill this in. Okay, I'll give you 2 or 3 minutes to do your own job. Of course, don't panic. The solution is there, right? So take it easy and see. The good thing is because we've put this minus verbose, it is telling you what each of these fields should be. I'll let you play with it a few minutes, and then we will see where you are, or okay. And those of you daring, you can try to run it. If I run it now, it's going to tell me all sorts of problems. You know, there's plenty of things missing here, so you've got to fill it before you can run it. And sorry, I forgot to tell you that I give you information up here, okay, about what I would like you to do. Okay, so we've created a model that drops the diffusion. Use your own value for M, N, Kf, and U, but be reasonable, okay? And then run it to steady state. And we're going to try to extract the longest profile, calculate to energy area, all sorts of things, okay? We'll do that together. So first, try to make a setup that works using your own value of Nx and Y, Lx and Y, something that makes sense to you. Uplift rate, and Kf, and N and M. And you know that if you use a grid shape of 100 by 100, it'll run fast and it's something useful. If you're very, very impatient, you can use 20 by 20, but it won't look very good. And you're very patient, you can put maybe 200 or 300 by 300. You can try a rectangular mesh, The thing about FastScape, and I'm talking as you work, and don't worry, don't have to listen to me, is that it is very, very robust, as we say. You really, really have to set very strange values for it to crash. Doesn't mean that it makes sense, okay? You can produce landscapes that have no physical meaning. Sometimes also when you give very strange values, the method that I use to solve the equation doesn't work. And so you get a solution, but it's not the solution to the equation. So that you have to be a bit careful.
John, one question. In the third part, when it says run it for a long time, with long time, you mean over 10 million years or?
Yeah, so, when I say a long time, it means the computation time. So if you take very large values for the grid shape, it will take maybe sometimes it can take 10 minutes to run a FastScape run. If you have 1,000 by 10,000, for example, you want to model the whole of Africa to get in one go. Okay, this will take 10 minutes to run.
Okay, sorry, I thought it was meaning others.
So typically you run it for at least a few million years, and you'll see, I strongly suggest you try to use the slope exponent of 1, and don't start with a reasonable value of m, because that will also make the solution look really strange if you don't use n equal 1, and you don't do, n equals 1 is safe, it's fast, and we should stick to that. But all the other parameters, just try anything. And once you have one and it's working, you can easily, don't do the next cell. I'm going to add another few cells. I'm going to run it. Okay, so you can copy that cell just after that one. And I will, even in the same cell, you can do everything in the same cell. I'm going to show it the solution. Okay, so I'm going to put this in there. You just copy and paste. And if you have a setup that runs, that works, that accepts, just run it and see what happens. As you work, I'm going to talk again, but there's something very important in Python is indentation. I forgot to tell you. Every line that you have should start with no blank here, okay? No tab or white space. It should always be indented left, except if a line finishes with a colon, okay? and then you should have an indentation. All the lines that are after a column that are indented means that whatever you've set that before the column applies to all those lines. Typically, when you have a for loop, for example, I'll make another cell to show you. So if I say for I in range 10, oops, 10. So you see I have a column there. So automatically it puts an indent for me. I can say j equals I plus 1. And then I can say print j. Okay. So you see everything that is indented will be done. But if I say, print j, this will only done once because it's not inside the loop. Okay. So it will show me 1 to the minus 10, and then I will just redo it again, but it won't do that 10 times because it's not in the loop. Anyone has been successful in running a model? It's a bit of a crash course. I know it's hard because they're also, you have to learn Python, some of you, and then you have to learn the framework, and then you have to learn FastScape all at the same time. So don't panic. There's absolutely nothing wrong if you can't do it in 2 minutes. Even me, when I started using Benoit's framework, it took me weeks to actually be independent. Did you manage to crush it, Caroline? Yeah. That's usually, Caroline, when you have you're giving an index to something that doesn't need one. Like you say x of 0, but x has not been defined as a function or as an array. Also, check that you use square brackets or round brackets where needed. Okay, a function has its argument are defined with round brackets. An array's index are defined with square brackets. And you see the way everything is defined here, where you give the name of something, a column, and then a value. This is because this is called a Python dictionary, I believe, and that allows you to associate a name to a value. And it can be very, this can be a number, this can be another string of characters, it can be the name of a function, it can be anything in a dictionary. So it gives you a lot of flexibility. Okay, I don't want to press you, but of course I want to move on a little bit, and I'm going to do it very, very slowly like I did it yesterday, okay? And you can check what you've done with what I've done, okay? So I'll go back to 1 only. And so I always start with the simple things that are inside here, and then I move into defining the clock, and then I move into defining the output parameters. So the grid shape, we know, it has to be. I'm sorry. It has to be 2 values, an array of 2 values, and I'm not going to be too smart. I'm going to make it 101 by 101. I don't know. Let's be adventurous. Okay. So it's going to be longer in the X direction than in the Y direction. Of course, if I make more points, I should make this longer. So I'm going to make it, 100 by 200 kilometers. Sorry. Okay. I remind you that the units in length is meters. So 1e5 is 100 kilometers. Okay. So we'll leave at the moment the fixed value. So this fixed boundary condition. We'll come back to that one. Uplift rate. Let's put 1 millimeter per year. Okay. We can put anything. Let's put 2 millimeters per year. Okay. Random seed. Random seed usually you leave none. What happens is every time you run your model, if you have no random seed, the white noise that's used for the initial topography will be different at every time. So if you put anything here, like 1, 2, 3, 4, 5, you're sure that the random noise you use to create initial topography will be the same every time. But you don't know what it is, but it will be the same every time you run this model. So I like to put 1e minus 5, 0.4. Okay? So I'll try that and see if it complains. And the first thing it says is, you need a clock. Okay? I don't have a clock, but everything else seems to be right. See, don't worry, don't hesitate about trying, and it tells you there's a problem. You're not going to break anything. Okay? So we know that we're going to define, usually we call it time, and this is the time step. So how often I'm going to calculate, at what intervals am I going to calculate the solution? So from 0, again, I'm not going to do 10 million years, and I want 100 steps, okay? And I think if I do that, it should accept it. Yeah, all right? So that's my basic thing, and I can run it and see what happens, okay? Just to have a look. And it tells me, I haven't put any output, so it can't show me the topography that I would like to see, okay? So, see, trial and error is the best way to do it. So we have to include an output. So topography, elevation, and I want it at time. It's not this, and I believe do this. No, sorry. Tack. Let's run it again. And still, why? Because I'm asking it with the time and dimension out. See, it's always an explanation here, and I have not defined a clock called out. So either the best, the simplest is to put time here, and then it will run and show me something. No, I have it out again here. So sorry. Okay. Tap. There we go. Okay. And now I have my, 200 by 100 kilometer mountain belt. It's pretty steep, very pointy. Can I ask you, why do you think I have such a rough topography? Anyone has an idea? Why is my topography suddenly so steep compared to previous runs? What is different? If you look at the parameters I've used, if we go back to the parameters here.
Is it because of the bedrock channel incision coefficient?
Of what, sorry?
Is it because of the channel incision coefficient?
Well, it's almost that, because we know that what determines the height of the mountain is the balance between the uplift and the incision. And so what determines, if you go back to the theory that we had here, okay, here, the height of the mountain, which is the scale here, is a function of u and kf. So you're right. If my kf is too small, I'm going to have an enormous mountain. But also, if my u is very big, I'm going to get a big mountain.
Yeah.
Okay, and so that's what I've done here. I've put 2e, minus 3. If I go back to 1 and run it again, okay, my mountain will look a little bit more reasonable. Okay, it's not as steep.
No, that's rough. So
and you look at the maximum topography I have now is 4,600, whereas previously it was almost 10,000. So this is a normal mountain. Now, I've written a paper one day that says the best way to constrain KF is to make a mountain that looks like a mountain. And there are not many values of KF that will do that. It's crazy, but that's maybe the best way to do it, okay? To constrain KF. Because we can estimate U from all sorts of other GPS or thermochronology, but KF is so difficult to measure in the field. And then the other reason why it's look a bit more peaky like this is because I've removed diffusion. Remember, compared to yesterday, there's no hill slope processes. Okay, now we've got something that works, and just if we look at the solution that I had here, which we are going to use because it's safer, so I'm going to put you guys on the side here. Okay, if we don't use this, but I suggest to make sure that we all have the same thing. Okay, we're going to use the setup I had there, which is a little bit different, and I want to talk about that. It's different in a few ways. First, I have defined an out, and I've only asked an out for the last time step. So I'm only going to save, because everything I save will be for the last time step. Okay, so it'll go faster. I don't have to worry about, I'm sure I will only look at the last time step. Okay, easy. The other thing that I've done, I've been really adventurous. I've used n equals 2 and n equals 0.8. But I had also to change the coefficient here so that my mountain is not too high. Okay, all these things is just me playing with the values of the parameters, blah, blah, blah. One thing that is very different, and I need to explain, is this, the boundary condition. I tell you, there are 4 boundary conditions because there are 4 sides to the problem. So to show you how this works, let me go back to this case here, okay? And I'm going to change them. Here, if you just say fixed like this, okay? It means that all values are fixed. But I can also give 4 values, an array with 4 values. Okay, that I'm going to fill now, that will allow me to have different values. So what I'm going to do is on 2 sides, I'm going to make them fixed. And on the other side, I'm going to make them what we call looped. Okay? So if you say more than 1 value, you have to give 4 because it expects. There are 4 sides, okay? You cannot say, I only want to say a value on 3 of them, okay? You have to give 4 values. It's either 1 value, which is then applied to all 4 boundaries, or 4 values, 1 for each boundary. And so fix, fix, loop, loop. Let's see what happens, okay? Let's just run it. Rather than me using words to explain what it means, let's just run it and look at the solution. What we have now is a mountain where only 2 sides, this one and this one, are fixed. And the other 2 are what we call looped boundary. And the best way to look at it is from the top, okay? What is a looped boundary? I'm even going to drive the vertical acceleration to 0 so we can see what happens. These looped boundaries means that if a river flows here, hits a boundary, it reappears on the other side. Okay? Every time a river comes here and hits a boundary, it flows out on the other side. It's a cyclic boundary condition. Okay? Obviously, when you say looped, you have to say 2 looped. There have to be 2 looped, otherwise it makes no sense. Okay? Good. So the other rule is that one of the boundaries has to be fixed, because a fixed boundary is where, if I go back a little bit of vertical acceleration, a fixed boundary is where the rivers ultimately go out. If you don't give 1 fixed boundaries, the water doesn't know where to go. It gets trapped, okay, in your landscape. You always need a fixed or base level for the rivers to exit. But there's another type of boundary, and I'm going to finish by adding that one. I'm going to put it here, for example, and it's a core boundary, or in mathematical language, it's a natural boundary. And why is it a natural one? That's we'll run it and see what happens with a core boundary. And a core boundary should always face a fixed boundary, otherwise we run into trouble. What is a core boundary? A core boundary is when a river cannot go that way. It's a wall. So if a river gets there, it bounces back. Okay? And so this is a classic way of doing a landscape evolution model, is to have one fixed boundary, one core boundary, and then two looped boundaries. And see what you produce here is half a mountain. Okay, half or one big catchment, if you want. Okay, it's more than one catchment. There's one here, one here. But you see how this river here, this guy here comes out back here and flows into this one. Okay, and this one here comes out of this one. Okay. So this is what I've done in this example that I've given you. I've got a fixed core looped. Okay, let's run this one now. And finally, I have to tell you what I've done here. And I don't have the time to explain to you. Yesterday we did this already. I'm getting the drainage area. But what I want also to get, and I remind you yesterday we talked about that, is the donor and receiver information. And we're going to use it in a minute. Okay? So let's run this and run the model and visualize it. And here we go. Okay, so this is a square model with the value of n and m and k. It's a reasonable mountain. And I'll be frank with you, I wasn't sure what to use for kf here. So I just tried a number and I got a mountain that was maybe 50,000 meters high. So I divided that number by 10 and I got a mountain that was 5,000 meters high. Okay, so that's the best way to play with FastScape. It's so fast you can do these things. We're all happy till now? Yes. Now, there's a cool way to do what I'm going to do now, but I don't have the time and I'll let you do it on your own. But, you know, FastScape, you have a landscape here. You could output it to a format like any kind of DEM format. And then you could bring it into your GIS system and pretend it's a real landscape. There's even a module to FastScape which allows you to extract any part of anywhere in the world, of the real topography of the world, and use it as an initial topography on which to run FastScape. Okay, so we have all this. I don't have the time to do this now, but typically when you have FastScape, you can output it to a DM format that you like, TIFF or whatever, okay? And then you can use all your tools that you have to analyze on a DM or landscape to analyze the fake landscape. And you can do that, of course, in the Python library, okay? I'm a very, lazy, so I'm gonna do something crazy. I'm gonna use actually some of the internal tools built into FastScape, like the receiver and the donor information, to find the biggest river flowing in this landscape and plot it. Okay? So this is what I've done here. And I don't have the time to explain you all this in detail. Please take the time at home to read it and see what I've done. But basically, I remind you, I've only saved the last time step. So all that I'm extracting from FastScape, from DS out, is at the last time step. And one of the things I've extracted is the receiver information and the donor information. The receiver is for each node, to which node I'm giving the water, so which node is downstream on me. And the donor information is the name of the nodes that have, so the donor of IJ, the node IJ, are the nodes that have IJ as a receiver, and it can be more than one. And then also I extract the X and Y of all the nodes, and I extract the uplift rate, the KF that I've used, the N I've used, the N I've used, okay? All of this I've put into the input file, okay? The input module, but the output ds out also contains it all. It's all been copied there. So that if you give me ds, ds out, I don't need ds in. Ds out contains everything, the input and the output. And finally, what I've done, and we're going to go very quickly through this, I've built a little Python tool. It's 5 lines long. It's very short. And let's open it. You can see it here. So if you click on it, it will open it here in a window. And in these tools, the most important one that we want to look at is this find largest river. Okay. So you see, I go back to the Python notebook that I was there. I import the tools as I call them TLS. And now TLS is a method called find largest river, or a function if you want, that takes argument area, the drainage area at every point, and the donor information. For every node, ndon is how many donors I have, and donor is the list of my donors. And having that information, look, in Python, it's really easy to find the geometry of where the biggest river is. Why? Inside the function, okay, I take area. So this is the drainage area of all the points on my landscape. And I find the name or the node that has the largest area. That, by definition, must be the outlet of the biggest river. That's the definition of the biggest river. It's the one that at its outlet has the largest drainage area. So I know the outlet of the largest river. I create a list, an empty list, and I add into that list ij. It's the first node that is the beginning of the largest river. And then I go through this loop here that simply says, okay, I'm going to take all the donors of the node ij, and among these 1, 2, 3, and 4 donors, I don't know how many I have, I find the one that has the largest area now. And I call it ij now. I overprint ij by the name of one of its donors, so the guys upstream from me, that has the largest area, and I put it on the list here. And I keep doing this until I'm at the top of the river, and that point, I know it's that one because it has no donors. Okay, I'm at the top, at the source of the river. And in doing this very simple loop here, I've constructed a list that contains the name of the nodes along the largest river. And from it, this is what I've done here, I can calculate the length of that river, that's S, okay? So that's the coordinate along the river, it's 0 for the first node, and it's L, the cumulative length at the end of the river when I get to the source. And I can also calculate the slope, okay? So what I'm going to do now, we're gonna run this cell, okay? And what it does, it plots using plot, it's this command here, the final landscape, but then it's simply plotting the river that we have just computed. And we know that this is the largest river on the landscape. You can, if you want to see it better, we can do color equals, white, so we can see it better. Okay, and we have the longest river along the okay. So you can do this using Topo2Lab or Topo whatever. There's all these packages that analyze DEM and extract things like the largest river on your DEM. Here, with this little, function here, I can do it in no time. So that's why I don't want to load another package and do this. We've done it here. And please use these tools the way you want. Try to understand them a little bit, but it's quite simple. And the next thing we're going to do now, of course, we know the geometry of this. So we're going to plot the height of the landscape as a function of the distance along the landscape. So the height of the landscape is a function of the distance along the river. Okay, and this is what we do here. Okay, so if I run this next, what do? I create a plot, which is plotting S, which is the distance along the longest river, and H of river, the height of the river. This is an array, okay, H of river, That gives me the height of the points along the river. River is the list of the nodes along the river. See how Python is smart in allowing you to do this. So if we do this, this is the comparison between the theoretical profile. So that formula here, okay, is exactly the same as this formula that we had it right at the beginning. Sorry, this one. And I've used this formula to get the analytical solution. And I know U, KF, N, and I'm assuming that P, the Haack exponent, is 2, and the coefficient is 0.67. And so I can compare in blue, or we can do a bit smarter thing, like, you know, label equals FastScape, and this one we can say label equals theory, and I think we have to do something like x.legends, legend, yeah, and then we can see which is which. So the blue one is FastScape, and the theory is the orange curve. Okay, and we see, well, it's not doing too bad, you know, it's roughly there, but it's not doing extremely well, is it? I mean, you know, I would say that my model is not doing a great job. It's got like 30% roughly, or 20% error, okay, compared to the analytical solution. So why is this? The answer is already written there, but if you want to think a little bit, what's the difference between running FastScape and the analytical solution? Any idea?
Well, my initial thought was that FastScape has more nodes along.
Yeah, that's very important that you have enough nodes. But I show the solution using 100 nodes, I think, here. Let me just check. Oh no, I'm actually using the same resolution because I do it using S, which is, you know, the same as S here.
Would it be the values that we use for M and N?
They're the same. You see the M and the N that I'm using for the analytical solution, M and N. I've extracted them from the output from FastScape. So they're the same.
We have the sediment input of the tributaries.
We haven't put any sediment model. That will come tomorrow, hopefully.
Because in the profile, the theoretical, okay, you are considering. Okay, I'm sorry.
No, that's a good point. We'll see, that makes a big difference.
Nice.
Well, the main difference, okay, I'll tell you, is that when you run FastScape, we compute the drainage area by looking at the direction in which the flow is happening on the landscape. Okay, so the drainage area at this point must be something, you know, follow this divide, must be something that was like this and like this. Okay, this is drainage area for that point. But if I go down a little bit, let's say I go down here, so maybe that, but suddenly at this point, bingo, I have a huge river that comes in here. So by going from one point to the next, my drainage area may be growing by 40%. And then a little bit further, there's another thing that joins here. My drainage area goes up by another, 10%. In the analytical solution, what we have done is use Haack's law. Haack's law says that, and I go back to it, drainage area is a nice and easy, smooth function of the distance along the profile. It just grows as S or L minus S to the power 2. So this is an approximation that FastScape doesn't do. FastScape calculates the drainage area for the landscape you're in. This is a general rule that, drainage area increases the square of the distance along the path, along the river. So to check how bad we're doing, what I've done in the next cell, okay, is compare the drainage area computed by FastScape, which I've extracted area along the river, to the theoretical prediction of hack. And if we run this, we see this, that, you know, this is hack. This is a, you know, parabola, a perfect parabola, because it's a square here. And this is the actual drainage area along the river. And you see where there is a confluence with another river, boom, the drainage area goes up. Here, 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 and there. One thing that I realize is maybe my K is a little bit too high. I can do a better fit. So if in Hack's law, I'm going to divide K by 2. Let's try this. The fit is already quite much better, okay? But you also see that, you know, the square, the P equals 2 is not a bad fit. It just doesn't have all these, you know, details here, okay? So let's put now here in my analytical solution, let's try to do a better fit by putting K over 2 and run, no, I adjust my hack law to what, you know, FastScape is telling me the real Hack's law is in the landscape. So I do it again for the analytical solution here. Let's run it again. I'm getting a much better fit already, okay? And I still have this infinite thing here, which we know is meaningless, okay? So you see, if the 1D model has the proper Hack law, the proper scaling of the Hack law, it does, you know, it predicts, or FastScape predicts really much the good analytical solution. One thing that is really, really interesting, guys, and there are papers written on that, it's a beautiful paper, I forgot the author, well, I should send it to you, that even though I have major variation in A along the profile is nice and smooth. And where you have a convergence of two rivers, there's no step. Where two rivers converge in the model or in nature, you don't see a step. You know, when you come from a tributary into a very big river, you don't have a waterfall. It happens at the same point. So try to think, why, no, come on, is it possible that even though I come with a tributary, there's a very small drainage area, I managed to get the height of the junction at the right height compared to this massive stream that's eroding much faster than me because it has a much bigger drainage area. And to make it even worse for you to think about it tomorrow, glaciers don't do that. I mean, if you ever been in a glaciated areas, when a small glacier meets a big glacier, there is a hanging valley. There's a big step. Okay, when the ice goes away, you can walk near Grenoble and look around. All the valleys, the tributary valleys from the glaciers, are standing up like you know, almost a kilometer up from the bottom of the valley. So rivers do that. They adapt the junction point so that there is no step. Glaciers can't do that. I had a little thing on the chi parameter. We're not going to do it because it requires too much theory and it's going to be boring, and I want to do other things.
Sure.
Yeah.
To do with the migration of nick points.
Yes, you can
in
do
glaciers. You have no nick points in glaciers, I would assume, right? So when you have a constant flow there, then you develop your nick points, and then somehow they find the balance. Yeah, that's why you keep these.
Yeah, and it's fascinating. We can do this experiment with FastScape. I'll design one tomorrow for you to show you. But,
oh, that's great. Looking forward to it already.
What is fascinating is, you know, if you take a landscape and then suddenly base level goes down, okay, you create a big cliff here, like the Messinian crisis, okay, and then that cliff, the nick point, is going to propagate because you have this enormous slope here, which makes the erosion really fast. But up here, you don't have this big slope. So this doesn't erode fast, this erodes fast. So that's why it stays like a step, okay? But what's fascinating is when it hits the confluence, it propagates without producing any gap again. The nick point goes through the confluence. It will slow down if it goes up the smaller tributary, but it doesn't create a step. It leaves no step behind. It leaves perfectly smooth river profiles, even at the junctions.
Okay, yeah.
Is the junction considered its own like local base level then for the tributary, and it adjusts to whatever base level?
Exactly, and that's the solution. And it's able to you know, the only you can create a temporary little nick point if you really have a nick point, it goes super fast. Okay, and then the river, the smaller, cannot really react to it. But you know, conceptually, even after, you know, it will create it adjusts its slope over a meter, you know, and then will relax it. Very, you know, this very simple, basic stream power law equation. There are still lots of papers written, even on the simplest form of it, on all its properties and a very bizarre behavior. Last thing I want to do with this notebook, and then we'll take I'll take 2 minutes, and then we'll take a break and come back on the next notebook, is the famous slope area relationship. That is the primary observation that, you know, our forefathers, geomorphologists, have used to derive the stream power law. Okay, and what they've done is they've gone on this landscape here. Okay, and at every point where it's possible, you measure the slope of the channel and you measure the drainage area. Okay, and you do that for as many points as you can, and then you plot slope versus area, or slope versus area. And if you look at the theory, if I go back here, okay, you have this relationship here, or this one at steady state. I think I have written it again in a better form, excuse me. Here we go, okay? At steady state, we have this relationship, that S is equal to a constant. If we assume uplift rate and Kf are constant, and N is a constant, S must vary as the drainage area to the power minus M over N. And you know that, you know, maybe I can do some LaTeX live. It's not gonna work, but I think I can do this. If I take the logarithm of S, okay, then I can write that it must be equal to the logarithm of, you know, UKF to the power 1 over M. Oh, sorry, I'm trying to be too smart here, but I think I can do it now. And let's look, let's do this is bigger, better. Minus M over N times the logarithm of A. And I think if I run this, it should work. Sometimes it lags a little bit. Come on, to interpret the LaTeX. Come on, here we go. Okay, so if I take the logarithm of this on both sides, the logarithm of S must be equal to the logarithm of this, and the logarithm of this times that, okay, is the logarithm of this times that is the logarithm of this plus the logarithm of that, and the logarithm of that is the logarithm of A times M over N. Okay, so you get this relationship. I've missed, there's a parenthesis missing here. But the key is that if I plot log S versus log A, I should get a line. The slope of the line gives me M over N, and the intercept gives me U over Kf to the power of 1 over N. And that's why M over N is called the concavity. And this thing here, U over Kf to the power of 1 over N, is called the steepness, or the steepness index. And the good thing with FastScape now is that we can measure the slope and the area everywhere on the landscape. It's super easy, okay? I don't have to go in the field or on a map to do it. So if we do this, I simply plot in a log-log plot area versus slope for all the points in the landscape. And if you run that cell, that's what you get, okay? You get area, slope, This is for the landscape I just, model this landscape, okay? I get an almost perfect relationship. It gets a little bit diffused at the end here. That's numerical noise. You start to see where, this is a very, very big slope. So near the divides, my algorithm is kind of having a bit of a problem there because it doesn't know what, numerically it's becoming imprecise. It's lacking accuracy. And what I can do even better is I can do a little bit of stats on that. Okay, so what I've done here is a bit of Python. I'll let you read it. You can do this in MATLAB, I'm sure. I do a linear regression between log area and log slope. And I'm going to print the slope and the intercept of the linear regression. And if I do this, for this set of data, I find that from the regression, the slope is 0.4 and the intercept is 100. And now if I look at my input, what is the concavity for my model? Well, it's m over n. And m here, what is it? M is 0.8, n is 2. So the ratio is 0.4. And if you calculate u, like I've done here, for the model, u divided by kf to the power 1 over n, you get 100. And so you see that FastScape, it's normal, it's solving the equation we told it to solve, okay? Creates a landscape that not only looks like a landscape, but it obeys Hack's law, more or less. We've seen this, it obeys Hack's law. It gives you a profile that's very much like a theoretical profile or a real river profile. And more importantly, it gives you the right scaling between A and S that every geomorphologist has measured everywhere on the surface of the Earth. So you could say, that's it. We can go home. We've solved the problem of geomorphology. We know how a river works, okay? No way, okay? There's so many other things. This is the ideal river, and I'm sure maybe one river in the world looks like this. But of course, there's a lot of variation on these. But you see that the fundamental shape of a profile, the slope area, the Hack's law, FastScape is able to reproduce it. FastScape or any model solving that equation in 2D. So it kind of builds a bit of confidence, but I know, because I work on this, that we don't know very much about things, in fact, okay? There's a lot of other processes we don't know. Good, so let's take a 5-minute break so you can stretch a bit or, go to the toilet or have a smoke, and then we'll reconvene in just 5 minutes and attack the next exciting notebook.
Yeah, I have just a small question.
Yeah, of course.
But you were mentioning how FastScape obeys Hack's law, but this would only apply to steady state situations, right?
Yes and no, it's true, okay? But what's interesting is that, if we go back to this model here, where I have saved more than one time step, okay? So I can look at the time evolution of it, okay? I move this so we can see better. Look what's really fascinating. I think I don't have the drainage area, but look at the shape of the valleys here, okay? The shape of the river network. And right from the beginning almost, see that river there, here? And look how it changes with time. Nothing changes. What it means is that in many rivers, especially when you have a fast uplift, once you have created a river, it's really hard to change its geometry because you have to erode the mountain that's between me and the next river. That's not totally true because there's something we haven't put in this, which is very important in the real mountain, is that, we are sedimentologists, so we don't really think about the tectonics of the whole problem. But what we assume here is that uplift is vertical. Okay, but that's not what's happening in the Earth. I mean, we don't have vertical falls and squeeze the Earth like that and it goes up like that. A thrust fault is a shallow angle fault, 30 degrees. So when you push like this, you create uplift, but you also create horizontal advection. And so think of it now. If I had put horizontal advection on my model, and it happens in the real world, that river here, that thing here, would be actually moving towards base level. And it's a very, very difficult thing to think of. But the shape, the bottom of the valley, you know, if you hit it with you put a peg. So you're right, the Hack's law, you need to check it at every time step. Here it's always right because once you've set the network, it's correct. It doesn't change.
Jean?
Yes?
In your, you said here you don't have the drainage area, and we had it on the other notebook, but when you look at the mini code you wrote just above, I have the impression it's the same. Do you know why?
Yeah. So for the second example, but for which I only kept the last time step, okay, see I've set my out clock to only the last time step. There I've saved the drainage area.
Okay.
See, my output vars. But the previous model here, which saves everything, that I started to build with you.
Yes.
I can do it, I can just put, drainage area. You're asking for that output. And I want it also at time. Okay, so if I run this now,
and now it should.
It will have the drainage area as a
Okay.
field I can look at.
Okay,
And the reason
I mixed
we
up
do
two
this,
codes.
the reason we specified output and not say is because FastScape produces an enormous amount of output, and if you say I want to store it all, you'd run out of memory on your computer. And here now, I'm sure if I look, I should have the drainage area. See, I have drainage area, and I can look at it. Then you see the rivers. Good. Well, we wait maybe for the others to come. I shouldn't do it, but looking at it, I think I want to tell you a little bit about this chi parameter. It's been introduced, maybe 10 years ago now, a bit less, by Perron and Royden. And it's kind of a mathematical things. Vicky Royden is a geologist, structural geologist at MIT, but she's an amazing mathematician too. And she came up with this bizarre thing that if you compute the drainage area on the landscape, okay, you assume a value for n over n, typically a half, that's what people use, or 0.4 or so. Then if you integrate, you calculate an integral of 1 over the area to the power n divided by n, and you calculate this integral from the bottom of the valley all the way to the top, you have a value chi, okay? It's called the chi parameter or the chi coordinate. And what's really, really amazing is, if you plot now the height of your landscape, like I've done here, but instead of using S or distance here, you use chi, okay? Which, you've got to have a twisted mind to think about doing that, all right? But if you plot H versus chi, they found out that regardless of the concavity, regardless of anything, okay, at steady state, if I do this, and I'm going to plot it for you, always, oops, it's not, it's that one, sorry, it's this one. Whatever you do, what have I done wrong? My mistake. I have to rerun the model because I've run it to explain something to. So I'll run the model again. I'll run the other model to explain something to Caroline. And now I can do this. Okay. So if I plot height versus sky. Oh, what have I done? I forgot to run the cell, but there we go. Sorry. That works. Now I can finally show you chi. So when you plot, I said for the 10th time, the height as a function of chi, bingo, it's a perfect straight line. Okay? And so there's a whole bunch of theory that was developed based on that. This chi parameter is really magic. You know, it allows you to check if you're at steady state very easily. Just plot your river profile, not as a function of distance, but as a function of chi. And if it's not a straight line, you're not at steady state. The other thing too is that if you have two rivers on either side of a divide, and if you measure the distance, the difference in chi between the two sides of the divide, the difference in chi tells you in which direction the divide is moving, if it is moving. Okay, so it's later that, you know, at another training camp, we will talk more about that, or maybe Sebastian will start this week, but it's a very interesting thing. And, you know, again, it looks like a complex thing to do, but in FastScape, because we have the donor and the receiver information, computing chi takes no time. And if you want, again, to look at the tools, there is a function that is find chi. And you see finding chi is one line of code. Very easy to compute. Okay? And I won't go into the details of this. If you want to have, you know, make your mind think about this, how Python works and how the donor and the receiver information work, look at this. Good. So, no more questions on this? Let's move to the really source to sing purpose of this whole thing. And what happened to a mountain when, or source area, when it rains on it and the precipitation, or let's call it the climate, but through precipitation, varies in a cyclic manner. Okay, and of course, when I talk about cycles, you right away make a reference to what Cecil told you, and Sebastian as well, that the climate of the Earth and many forcings on our systems are cyclic. You know, Cecil showed you these first order, second order, up to fifth order cycles, okay, that people have extracted from all sorts of data. And we also know that, you know, thanks to the Milankovitch theory, that there are known cycles of the climate of the Earth that are related to the insolation we receive from the Earth, from the sun. Okay, there's one at about 20, 21, 40, and 100,000 years. Okay, but there are much longer periods. We believe there might be one that's associated with the, you know, our solar systems going through the arms of the galaxy, where it has a higher density of supernova, and there's more radiation hitting us, and therefore there's more potential for creating more clouds, and therefore this is one way that people explain this very long-term 250 million year cycle in glaciations. I'm not saying it's true, but there are many, many, many potential cycles in our climate. So what we're going to do today is run a model and change the climate as a signed function of time, okay? And I'm going to show you also by doing this, by using a really, really cool feature of FastScape, that if you understand how it works, it opens you the potential to design very complex model, complex of arbitrary complexity, basically. Even though, if you look at the input, it's just 5 parameters, okay? Now, before I do that, I want to tell you also that I'm a physicist, okay? So I was trained as a physicist, and I like to study systems. And I'm going to take a system, is something for me that has an input signal and an output signal. And I'm really interested to understand how the system works, how the output compares to the input. And to do that, physicists, they usually say, well, as an input, we're going to put in a wave, a sine function, and the output is most likely going to look like a sine function. And I'm going to compare 2 things: how the amplitude of the output compares to the amplitude of the input, and we're going to call that the gain. Think of it, that's the amplitude of the wave you listen on your stereo compared to the amplitude of the wave that was put from your iPod into the amplifier, okay? It's the gain, it's the volume of the output compared to what you put in. And the other very important thing is the time lag. If I go up in the input, is the output going up and down at the same time? Or is there a phase shift between the two? They could be totally out of phase. They could be slightly delayed, okay? Rarely in advance. It's very difficult for a physical systems to produce a signal that actually is predicting the input, okay? So we're not going to consider that. Okay, so let's do that in FastScape. And I'm going to just show you the input file here. Or I shouldn't say call input file, the input cell, okay? And let's look at it. What's different, okay? Well, let's go through it. I've defined a clocks and I've defined the time steps in the cell above here. We're going to go through this. But that's something we know, okay? We have defined a clock, we called it time. Grid shape is 100 by 100. Grid length, I've defined a length, L. Again, I've put it here. So L is again defined up there. And I've put these boundary conditions, fixed co-loop loop, you know what it means. And I have a U here, which is the uplift rate. I have a coefficient KF, an N, and I'm asking to look at the topography, and I'm asking to look at the topography, the output at the same frequency or at the same time step as the input. Okay, so, well, nothing has changed to your problem. It really looks the same. One big difference, though, is that this and this are not single values. They are arrays. So this is fascinating that when you give a single value to FastScape, you say, well, it's just a constant. So if U is a constant, it will assume that in space and time, U is a constant. But if you say U will vary, and you give it, if you want, for example, to say U will vary spatially, then what you have to give to FastScape is an array that has the dimension nx by ny, the shape of your landscape, and it can have different values in that array. Automatically, FastScape will understand, oh, it's nx by ny, so it must be a spatial variation, and I will use it as a spatial variation. If you want to make it vary with time, then what you say, you give it an array that has the same dimension as your time dimension. And automatically you say, oh, that must be a time dimension, so I will do that. And you can even, it will use the same value everywhere spatially, but will make it vary with time. And finally, you could say, oh, I want a very complex model where U or K will vary in space and time. So you need to give him an array of dimension nx and y, number of time steps, a 3-dimensional array. And automatically, FastScape will figure out, oh, it will vary through space and time. And you can see that now what you have to do is to build these arrays that corresponds to your problem. Okay? So what I'm going to do here is simply assume that there is a change in precipitation. So I will keep the uplift rate a constant, but my kfxr is going to vary with time. Okay? And if I do that, when I say kfxr to FastScape, it will use a different value of kf at every time step. That corresponds to a different precipitation, and it will do it properly. Okay? So to do this, we can go through this cell together. You know, I'm not going to type it all, and let's look at it. Well, I'm defining here all the parameters as variables, n, kf, u, and l, and I'm going to put them here. Okay? So L, big L, petit m, right? You see they all appear here. So what are they? M equals 0.4, n equals 1, kf 10 to the minus 5 as usual, u 10 to the minus 3. Let's just take this, you know, basic numbers that, sorry, we know give us a good mountain, and I'm going to assume a square model, 100 kilometers by 100 kilometers. Now, I want to define now a function that represents precipitation. And what I'm going to do is, I'm realizing as I'm telling you now that I shouldn't have done that, but I did. Okay, so don't worry. What I'm doing is I'm going to assume that the precipitation is constant for 10 million years. And then after 10 million years, it's going to vary like a sine function above and around the mean with a period, okay, the period of oscillation of 1 million years. Okay, so let's try to build such a function. And I'm going to call it precip. Okay, so precip, what is it? It's 1 plus 0.5 times the sine. So it's going to be 1 plus or minus 0.5. So I'll have a 100% variation compared to the mean, times the sine of 2 pi times the time minus 10 million years. So I'm only starting the oscillation at 10 million years. And this divided by the period of the oscillation. I remind you the formula to create a sine of a given period is sine of 2 pi t divided by the period. So 2 pi times t, I only want them to start at the equilibrium time after 10 million years. So it's time minus that divided by the period. So that's my precip. Okay? And tin, or tin here, is time. So I have to define it, and time is 100 point from 0 to 10 million years, and another 100 points from 10 million years to the t final, t final, and t final here is 5 times the period past 1 million years, 10 million years. Okay, it's going to show. I'm going to show you that function in a minute, and you'll understand it. Sorry, I have to run this cell first. It'll be much easier to understand what I've done. Okay, so it's this function. It's 1, and then when I get 10 millions, I have 5 periods of 1 million years. Okay, and so what I do next is I say that I create an array, which I call KF, TIM, which is the product of this precipitation times my reference KF. Okay, the KF, which I said 10 to the minus 5. So now I multiply KF by the precipitation to the power m. Okay, and I remind you that's because that's how the precipitation rate is into KF. It comes to the power m. And finally, what I need to do, which, you know, you need to learn that when you use FastScape, but it's a habit that comes very quickly, to tell FastScape that this has the dimension of time, you create it this way, and you say, look, I create a next array, a data array, that contains KF-TIM, this varying KF, and I tell it it has a dimension of time, so that FastScape knows that it has to treat it as a time dimension. Okay, so it's a bit complicated, but it's you know, because I have to explain it rapidly, but, you know, it shows you how you can build a function that you put as an input to FastScape quite easily. So now, if I run this, of course, it runs without, you know, easily, and I'm going to run FastScape here. One little thing that I want to tell you, this is not important. I told you that you may want to save a lot of information out of FastScape. And here we want to start to store the solution at all the time steps, and we may have a lot of time steps. So what happens if you do this, FastScape tries to keep everything in memory. And your notebook, you know, if you have a very big model, is going to run out of memory. As there are limits on how much you can put in a notebook. Okay? So what you must do, and this is another thing that Benoit worked really hard at, it's super simple. When you run FastScape, you know, you have this DSR, Descending Lab Run Model, SPL model, you add this little thing called store equals Z group. And Z group, you've just defined it here, is a file on your disk. And so when I run this, you see, when I run this, it's created this file now, output.zar. It's actually a directory, it's more than a file, but think of it as a file. And now when I'm going to run FastScape, rather than trying to keep everything in memory, as it calculates stuff, okay, it puts it into the disk and doesn't keep it in memory. For you, it's totally transparent. It looks like everything is still in memory, but it, you know, helps you not crashing your notebook because you would use too much memory. Okay, so I'll repeat while it's running, so it takes a bit longer here, that what we've done is created an array that contains a time-varying function, kfxr, which you had to dress a little bit by giving it a dimension time. That's what it looks like. And we've put that as one of the parameters for FastScape, which it will then understand is a time-varying function. Why is it taking so long? It shouldn't take that long. I'm baffled. Let's see what the output looks like. It should run as fast as the other ones.
Mine finished, but doesn't work.
What do you mean?
No, mine doesn't work either.
Like it's at 100%, but it doesn't show anything.
Wait, let's see what happens here. Good. And if I run this now. It's working. But it took so long, it's strange. There's something fishy here. What have I done wrong? I'll check it while, you know, later, but let's look at the results now.
Caroline?
Yeah?
No, because Caroline said that hers didn't work, mine didn't either. I just run it again and now it works. So maybe.
What did you do? Sorry?
I just run it again and it works now.
Okay, okay.
It's strange. Maybe because I'm trying to write to disk and within this Docker, there's a problem, but I'll check it for you tomorrow. So what do you think is going to happen? What do you think if I play the life of this origin in front of you? What is going to happen? You should know. If, let's say, okay, if it rains more on a mountain, what happens to it?
Get increased erosion and sediment transport, but I'm just not sure with the time scale, how long. I guess you're going to see your mountain fluctuate.
Oh, yeah, very good, Amanda. Yeah. So, you know, if it has the time, what will happen?
Will flat.
If it rains more, the discharge in the river is going to go up, So because the uplift hasn't changed, to balance, for the erosion, to balance the uplift, because you have more water, you need less slope. Okay, so if you rain more on a mountain, it shrinks. And if you rain less, the mountain will grow up because you have less water, less discharge in the river, and you need more slope to get the uplift right. Okay, so let's before I show it to you, let's think a little bit more now. Let's assume I remove, I rain less. Okay, I'm telling you that the river, the mountain, will need to grow to adjust its slope. Very basic question. How fast? What's the maximum speed at which it can grow?
The uplift?
The uplift rate. Okay. So your question, Amanda, is the answer to your question is, it depends. It's going to depend, can it react fast enough? It's going to depend on the uplift rate. It's fascinating, isn't it? So let's play this, okay? And this is what we see. I don't know if the Zoom can refresh fast enough, but what you see is you grow to this steady state. You remember the first 10 million years, nothing happens. Okay, so we're about 7 million years, 8, 9, 10, and now the precipitation is changing and it's not working. So that's why I think there's something wrong in my input file. What you should see is the mountain beating. What is wrong with this thing?
I guess we could see, just it was subtle. But I guess we could see, but it was subtle.
Yeah, it was too subtle.
You could see a little bit of oscillation.
I thought I had chosen the parameters, so it wouldn't be that subtle. Okay.
Maybe if we just put more exaggeration.
So maybe it's the right solution. So how can I make it less subtle? I have two options. Well, maybe Amanda was right. My variation are too fast. The mountain doesn't have the time to change its height. So I have two options to make the mountain react to it.
The weather cycles could be longer?
Exactly. Or I could change the time it takes to react.
Yes.
By making the uplift rate much faster. So it can react faster. You see? So let's do the first thing, and I hope it will run faster this time. But now let's go back to where we defined the function, and instead of a period of 1 million year, I'm gonna be really bad. I'm gonna say a period of 100 million years. Okay, so there I'm sure that I should see the mountain change. Okay, it has plenty of time to change. Okay, so let's do that. Still don't know why it's so slow. I'm really sad that it is so slow. I'm so proud of FastScape being fast that when it goes slowly. Okay. Now you notice now that look, this is 10 million years. Okay, to get to steady state, and now I'm going to run this for like 1 billion years. Okay, so this is very long cycle. No, there is no mountain on Earth that will last for 1 billion years. We know it's not makes sense. We are physicists here, all right? So we're just checking that it works, that it should do what it does, what it should do. So we'll wait a little bit. And while it's doing that, I will strongly advise you, because now we have to stop, now it's 5, to play with this notebook and play with the period, play with the uplift rate. And tomorrow, what we're going to do is run, we're not going to do it now, it's too, I don't want to do this, I need the time to do it, because this, what we do next, is the way to look at source to sink system. We're going to plot how the flux out of the mountain varies and compare it with time, and compare it to how the precipitation that we impose varies through time. And we're going to compare the gain. Is it amplified? Is it decreased? And we're going to see if there are any offsets. Okay, so let's just do it quickly here. I'm not looking at that, but just look at the solution as a function of time now. And hopefully with these very long cycles, so we still have the first 10 million years, and then time is going to accelerate enormously. Okay, you're going to go through then a billion year when you hit 10. Okay, so from here, and now there you see your mountain be breathing, going up and down. I'm not going to give you the solution, but it doesn't look, even though my cycles are about 100%, it doesn't look like the mountain is going up and down by 100%. So I'll let you think about why it's that. I'll play it again from here. You see, it's not going up definitely by 100%. And that's the whole point of what we're going to do tomorrow. Okay, so remember, this is a model. Okay, but we've seen that the stream power law produces stuff that looks really much like real mountains. So I'm not going to tell you that this is exactly how a mountain will react on Earth. But if we look at things like the integrated flux coming out of the mountain, maybe, drainage density, the height of the mountain, all this should make sense compared to the real world. I'm not going to tell you that the details of everything on the model, we can compare it to a mountain. Okay? You have to remember that you can get out of a model what you put in the model. And all we've put in it is say that erosion rate is proportional to drainage area or discharge in the river and slope. That's all we've done. And if there's any reason for this not to be true, then this has no sense. Okay? Good. Any questions?
Jean, I had the impression that higher slope areas did vary a lot more, and closer to the bedrock or closer to the base level, they pretty much.
Yeah, there's actually a whole school of people. I don't want to look condescending, but there's a people who spend a lot of time studying these, because these slope area relationships are very much telling us a lot about the details of the stream power law, or where it doesn't work and why. And you're correct. In fact, in many cases, there's usually definitely a departure from this, and we can produce it with FastScape if we add the diffusion component, for example, where if you get to this steep slope, it breaks down, it turns around like this, and then at some point it goes down like this. Okay, and that's as you go towards the divide. Okay, so as you go up towards the divide, you're steeper and steeper, but at some point you can't just continue to be steeper. Okay, what happens is that you go the other way around, because the divide is a feature in that way. And as you go towards the divide, obviously the slope has to decrease, because at the top the slope is 0. So the point at which you lose this linear relationship is where colluvial processes take place, and the stream power law, you're still trying to incise, but there is stuff coming from the hills that starts to really matter now. And your erosion rate is really, or your capacity to remove stuff, it gets decreased, not sufficient. And you slowly move towards another process, which is landsliding, soil creep, whatever that's happening on near the divide. But also we are writing a paper now with one of my former students on the effect, and again, FastScape can do that, but I don't have the time to show you. But we can look at the effect of discharge variability. That's the daily variability in discharge. And you can show that if you have a river it's not a good example because it doesn't incise into bedrock, okay? But if you take a river like the Amazon, it has a very large mean discharge. but the variability, the day-to-day variability is very low. But if I go in Grenoble and I look at the Isère, you know, I used to live next to it. I mean, it's a torrent, it's a mountain torrent. And I can tell you there that between, you know, the spring snow melt and the middle of winter, the discharge varies by a factor 100 to potentially more. Okay, so rivers that have a small mean discharge usually have enormous variability, and rivers that have a very mean, large mean discharge have very little variability. And when you feed that onto a model of erosion that has a threshold, that means that you need at least a minimum discharge to do any work, then it becomes very important of how the discharge variability is, how big your river is and how variable it is. And if you put that in the model, the way to see how different it is from this normal model, which doesn't take into account the discharge variability, one of the ways is to look at this curve. And you can show that the curve looks very different and may explain some observations we have in some rivers where this doesn't work. Okay? And you know, you find actually that there's a slope here where you are near that threshold area or threshold discharge. Okay? So, you know, it's as I said, a simple equation, but people have spent the last 20 years or so trying to prove it and at the same time improve it or disprove it as well. And if you want to read, I think, again, I think I have that in, and I'll finish on that. Is it here or in the other? Sorry, I just quickly, it's my last word. No, it's this one, the one we did today. I think I've put a reference here. So, no, I haven't. But I should have done that. So there are these classical paper on the stream power law, okay, which you should read, blah, blah, blah. But a really good paper to read, which will give you reference to all the classical one, is a much more recent paper by Dimitri Lag. I think it's in 2014. Okay, so if you tap Lag 2014 stream power law, you know, you'll get it. Okay. And it's basically telling you what is the stream power law, how we can test it, how it fails some tests, and how we can improve it. So it's a really, really, really good paper from a geomorphologist with a lot of data into it. So I strongly, you know, it's a long paper. I think it took me almost 2 weeks to read because it's really dense, but it's got a lot of good information on the stream power law. Good. Okay, thanks. So I'll see you again tomorrow, and we'll finish this and then go into the basin, the sink, or the transfer area, sorry. Okay.
Thank you very much, Jan.
Bye-bye, and have a good evening. I don't know if it was recording or someone is recording or stop recording. It's still recording, so.
Yeah, I care about the record.
Thanks, François. Merci.
Thank you, Jean. Bye, everybody.
Bye. Good evening, everyone.
Thank you. Bye-bye. Merci, bonne soirée.